Hello and welcome to part 2 of Unit 15. In this part, we're going to cover Pascal's principle. Pascal's principle says that if you change the pressure to an enclosed fluid, that change is transmitted undiminished to all portions of the fluid and to the walls of the container. So let's give an example. Let's consider two pistons. So here I have a small one and a large one. If I push down on this piston, then I am applying I'm changing the pressure in this portion of the system, but that's transmitted everywhere. Since the pressure has to be the same and the areas are different, then my two forces have to be different. Okay. That's what we're talking about with Pascal's principle. And it has a lot of really neat application, as you can see probably from here, hydraulics, but it also allows us to think about what's going on with blood pressure and things like that. So let's do an example. So our first example is we're going to use a hydraulic lift for a car. Okay. In our hydraulic lift, we have placed a small car. This is a pretty small car. It has a mass of 1,000 kilograms, and it's lifted. And what we're told is the plate under the car is 10 times larger than the plate at the other end of the hydraulic lift. So what are we looking at? We have something over here with a plate which we can put a force downward on. And that comes over and expands outward somehow with another plate, and on that other plate is our little very poorly drawn car, but you get the idea. It's supposed to be sitting on it, not floating, right? If we push down on this, then this is going to go up because of Pascal's principle telling us that the pressure has to be equal throughout. Okay, so I'm going to call this side the car side, and I'm creatively calling this side the small plate side, or P. And what Pascal's principle tells us is that the pressure on the two plates, the one with the car on it and the one on the other side, has to be equal. So the force on the plate side divided by the area on the plate side has to equal the force on the car divided by the area of the car plate. Okay. Now we're told in the problem that the area of the car plate is 10 times the other area. So we can plug that in. And you can see we have the area of the plate on both sides. So that allows us to immediately determine how large a force we have to put on our little plate in order to lift our car. The force we need to apply on the car, or the force we need to counter on the car, is its weight, which is mg. So we'll have mg divided by 10. The mass of the car is 1,000 kilograms. Acceleration due to gravity is 9.8 meters per second squared. And we're going to divide that by 10. Which gives us a total force we need to apply equal to 9,800 newtons, right? So in order to lift our car, we have to apply a force, in this case, that is 10 times smaller than its weight, which is a pretty nice result. Still a large force, though. Okay. Pressure comes in a couple of ways. And one thing we need to think about is what's the total pressure, or the absolute pressure. Okay, so first off, we're going to talk about gauge pressure. You might think of like a tire gauge. It's designed to read 0 when it's just open to the atmosphere, nothing doing anything to it, if you will, like a tire gauge. This gauge pressure will be positive if our pressure is above atmospheric pressure, and it will be negative for pressures below atmospheric pressure. Tire gauges typically don't read negative because we don't typically pull a vacuum on a tire. Just saying, right? Okay, atmospheric pressure is the hydrostatic pressure of the atmosphere above you. And remember that this has a value at the surface of the Earth of 101,325 Newton meters squared. Okay, and then the absolute pressure is the total pressure, which is the combination of these two things. You have to take atmospheric pressure and add it to gauge pressure. Okay, we're going to do an example that is related to this, but not exactly this. Okay? And so we're going to return to the example that we started last time, which was thinking about what's going on 10 meters below the water surface. So in the last unit, or last part of this unit, we found that the pressure due to the water at a distance 10 meters below, remember we calculated that with a rho GH, density of water was 1,000 Newton per meters cubed. Sorry, I blanked a minute for what kilogram per meter cubed. I blanked on the units of density. Gravitational acceleration is 9.8 meters per second squared, and we have 10 meters of water, and that was how we got to the 98,000 newtons. The atmospheric pressure, I've given this number a couple of times now, 101,325 Newton per meter squared. I guess I should finish my units up there as well. So what is the total pressure experienced by this scuba diver? The total pressure will be the pressure of the water plus the atmospheric pressure, and that works out to be 199, oops, too many nines, 325, there we go, newtons per meter squared. Okay. Moving onward. Cool application of Pascal's principle is thinking about a manometer. A manometer is a blood pressure cuff, right? Or that's what a blood pressure cuff uses, right? So how does this actually work to measure your blood pressure? So what we have is we have a system. That system consists of the cuff here, right, which we can pressurize. So we're going to put in pressure with that little ball that they squeeze. Okay. And it's also connected to a tube, typically of mercury. And courtesy of Pascal's principle, the pressure throughout this whole thing has to be constant, right? So we're applying the same pressure to the main artery in our arm and to the column of mercury. Okay. If the applied pressure is big enough, or in other words, if it's bigger than your blood pressure, then no blood can flow. And so the first thing that the nurse or whoever is taking your blood pressure does is pump up the cuff until no blood is flowing. And then they slowly let it out. And eventually, as your heart beats, you're going to start seeing fluctuations in the pressure applied here. Because you've got blood starting to flow. So it's getting a little bit looser and tighter as your heart beats. But that, because the pressure in this cuff has to be constant, with everything else in the system, that's going to cause the mercury in here to fluctuate up and down. Okay? The point where that first starts is called the systolic pressure. And then they keep decreasing the applied pressure in the cuff. And basically, they do it until that fluctuation in the mercury stops. So they no longer see it going up and down. And that is your diastolic pressure. Okay, that completes this unit. And in the next unit, we are going to be discussing Archimedes' principle.